third time in 5 minutes, and we're going to talk about some math. So tonight we're going to talk about exponential and logarithmic basics, which means I'm going to talk about the different properties of exponential and logarithmic functions, being able to convert between them, and some logarithmic properties. I'm not going to go into equations tonight. I'm just going to go over the simple basics of exponential and logarithmics. Mostly for the fact of ACT should be coming up within the next month, and this is an area that generally isn't covered in Algebra 2 and pre-cal classes as of yet. So it gives me a chance to go ahead and cover that. So if you're one of those people getting ready to take the ACT, then this gives you a little bit of a heads up. I'm going to try to do ACT like readiness things that I see throughout, I guess, the weeks, the months, the years that people struggle with going into the ACT. So today we're talking about the basics of this. We'll probably go into some equations sometime soon, and then maybe talk about some different like ACT type word problems in the coming weeks. So I kind of have an idea going forward of what we're going to be doing over the next month. So hope you're looking forward to that. Track season started, so everything's getting really hectic and busy, so I'm trying to have a plan. But tonight, Mathman Monday presents Exponential and Logarithmic Basics, and I'm happy to be back. I'm your host, Blaze, the Math Man. So let's get a talk about exponentials. If you don't know what an exponential function is, if you've used exponents, you know what an exponential function is. You just didn't know it. So to start off with, we got all of our markers over here. Bamboozle. When we talk about exponential functions, we have this idea that an exponential function is just a number or variable to some power. So the easiest thing that I always like to talk about is f of x equals 2 to the power of x. And generally what you're going to do here is you're going to go into your handy dandy calculator and you're going to plug that in, and it's going to give you a lovely graph. Well, fortunate for you, I don't have a calculator, so we're going to work this out. And you're going to go and do these just like you do your other functions to make an XY chart. And you're going to look at -2, -1, 0, 1, 2, and 3, if we can fit it down there. And basically, you're going to work each of these out and say, well, I know that if I do 2 to the -2 power, I get a value. 2 to the -1 power, I get some value. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3, right? All I'm doing is I'm substituting these x values that I've picked in for x to find a y, then be able to graph it. So if you haven't dealt with negative exponents in a long time, or just not at all, let's talk about what you're supposed to be doing. This negative exponent lets you know this base value. So 2 is our base. So there's no confusion. 2 is our base. And this base value gets squared, right? But this negative exponent lets us know that means that base is going to flip. It is right now in the numerator because it's 2 over 1. It is going to flip to the denominator. So 2 squared is 4, and that becomes 1 over 4. That makes this 1 over 2. Anything to the 0 power is 1. Anything to the 1 power is itself. 2 squared is 4. 2 cubed is 8. All right, so you just found all the values that go here. 1/4, 1/2, 1, 2, 4, 8. All right, nothing particularly crazy, I hope. And once we do that, we're going to come over here and we're going to graph this lovely thing. And really, we don't even need the bottom part of the graph, but we're going to have it there anyway. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, cool. And we're going to graph this function. So you're going to go, and I know it's really hard to graph functions, so, we're just kind of winging it. You're going to get really close to the x-axis at -2. A little bit further away from the x-axis, and then you're going to get on 0, 1. Sorry, where was I at? Yeah, 0, 1, 1, 2, 2, 4, 3, 8. Should be like right here. All right, and the reason it's called exponential function is it grows really, really fast. Some would say almost exponentially. All right, and this x-axis works as a horizontal asymptote. So you're always going to get really, really, really close to this x-axis, but never touch it. All right. And you go off exponentially. Every exponential graph looks very similar to this. You could obviously talk about some different transformations, such as we had negative x, you get a reflection. If you had x minus 2 up there, you'd shift everything left 2. If you had 2 to the x power plus 4, then you're going to go up 4. And those transformations can all affect it, but overall, you get this general idea of this graph. And the good news is your logarithmic graph is sort of similar. So I don't like to spend a lot of time on graphing because more often than not, you're probably using a calculator to graph at this point, especially with exponentials and with logarithms. I hate to say that because I'm a person that likes to work all these out by hand and show people how to do it, but you're just doing an XY chart. This shouldn't be anything new. If you've gotten to exponentials, you should have already done graphing, hopefully linear, quadratic, and hopefully other equations as well, like absolute value and cube equations. If not, please go back and review that and then come to this, because that's going to be helpful with just talking about these XY values that happen. So with our exponential functions, this is the general setup, and we can go and relate that once I find my eraser that I did something with. Where did it go, guys? Ah, there it is. Over here looking around. It's right next to me. We're going to relate this in another way and relate it to our logarithmic functions. So that's a basic exponential function. There's not really a need for me to go much further into that because more often than not, you're going to be programming those and not doing them by hand. The general idea for a quadratic or for exponential functions is written as follows: a to the y power equals x. Now, this is really, really dumb because when we talk about logarithmic functions, you have this idea that log base a of x equals y. Now, the reason I don't really like this is I don't know who ever decided on exponential, and I know the reason for it is because you always set up your graphs as y equals. But man, is it hard for people to get the idea of a is not, or x is not exponent. So they could have done me some favors and not had that happen. But let's talk about converting between the two. These technically can be both moved to one another. If you want to go to exponential to logarithmic, so if you have exponential form and you want to go to log form, all right, you take your base, which is always the base. All right, it's the base here, it's the base here. You take your base, you raise it to this power, and it equals, actually I set it up in a way this is going to work out, haha. And it equals there. So you have I lied. So you start off, when you see this, rewind. Actually, don't actually rewind. I'm rewinding in time. You have a, which is your base. So you have log base a, right? Because we're converting to a logarithm. Log base a of x equals y. All right, this little circle has helped me so much and allowed people that had an issue understanding logarithms a way to understand them. So, right, so if we go from there, if we're going the other way and we say, hey, I want to be able to go to log to exponential, we can make that happen by doing the same idea. Your base to the power, so 2 power is x. All right, is the same thing as equals. So a to the y power equals x. All right, and you can see these in many different forms. You could see them where they actually just want you to convert. You could see an exponential function given. They want you to solve it out. And we'll talk about a few different examples, but I want to make sure we have this conversion. And I'm going to set this board off to the side so we can come back to it here in a few minutes if we need to. Right, so if we're over here and we're like, hey, let's talk about some different problems. Now, if we're talking about just exponential functions, we see some other things, but we have like a variety of problems that we like to see. So like you'll see things like, hey, how about 10 to the negative 2 equals, or I guess I should say, let me write out the instruction. We'll do 10 to the negative 2. Find the value of each exponent. So you'll have one that's like maybe like, hey, 10 to the y equals 1 over 100. B. 5 to the y equals 125. And I'm doing things we can do by hand, by the way. So, sorry, not sorry, I guess. C equals 4 to the y equals 256. All right. And you could solve for these y values. Now, you could do this in a calculator, but you could also go, hey, guys, well, I have 10 to the y, and I need to get 1 over 100. Well, y then has to be some type of negative value, and 10 squared is 100, so it's y equals negative 2. And then I say, hey, how many times do I need to raise 5? What power do I need to raise 5 to get 125? 5, 25, 125, so 3. Y equals 3. How about 4 to 256? Well, 4, 16, 64, 256, so y equals 4. All right, so you have these like basic idea problems where you do that. That's nothing too crazy for us. Those are usually pretty simple. Usually my students look at me like I'm crazy when I bring those up, and they're like, how does that work? Like, why is that so easy? I'm like, because it's exponents and exponentials. If you're paying attention to what you need to do, this will never be too bad. All right. You then have convert. To logarithmic form. So you might have x to the third equals 12, or x to the z equals t. All right, you might have just random variables. You might be given numbers. All right, key word is they asked you only to convert, not to solve. All right, if they say convert, that means all they want you to do is change this exponential function to logarithmic, right? Which, going back in time, means we're going to take our base, log base of the value on the other side of the equals, and then equals the exponent. So log base of x, log base x of 12 equals 3. Log base x of 12 equals 3. All right, easy peasy, nothing crazy. Do the same thing down here. Log base x of t equals z. Log base x of t equals z. All right, those conversions are really simple. You could go the other way with logarithmic and go convert from logarithmic to exponential. All right, and you might have you have log, and if they, I guess I'll write that out in a second actually. Log 6 of z equals 72. B log base z of x equals y. All right, again, you can follow the same idea that we wrote out on our previous board that says, hey, if I want to go from logarithmic form to exponential, my base gets raised to the power of the what's on the other cycle. The equals is the of. So 6 raised to the 72th power is z. So 6 to So the 72 is z. That is a large number. Hey, if you do this problem, find out what z is. Leave it in the comments. Log base z of y. So, z raised to the power of y is x. All right. Easy peasy, lemon squeezy, as my 4-year-old son would like to say. All right, so let's talk about some other things to deal with logarithms. That gave us the general idea of the basics of converting between exponential and log. You can figure out how to solve those given that information, how to solve basic exponential functions. But let's talk about a couple of other things that come up. So there's actually a common logarithm value. So you have the common log, and the common log says if I just had log x, all right, log x is something you can put in your calculator. You can hit log, press, or I guess you could say 15, doesn't really matter, but you can say the common base here is 10. Hey, Anonymous 12, I'm doing pretty good. Just teaching some logarithms and exponential functions. So your common base is 10, and then you can look at your natural log function, which comes about later and actually ends up with a different notation. But natural log is a logarithm. Nothing too crazy. So if you have log base e to the x, and we haven't talked about the number e yet, but this gets converted to natural, I better not write a h. Natural log of x. The thing about this is we have e, which we haven't discussed yet. The number e. That's right, I said the number e. Because in your fancy dancy calculator, e has a value of 2.718281, I believe. Those two might be swapped. I don't remember off the top of my head. Seems about right. So anytime you're dealing with e, we have another log base. And the reason we bring up e is if you're doing any type of compound interest problems, growth rate, exponential decay, half-life, use all these different values, or even doubling time for interest rate problems, you end up seeing e, and e has this set exponential value. And then you can take that and put it as a base of a logarithm and use natural log. What ends up happening is this allows you to manipulate some equations to find doubling time, or find a constant or a time or a rate that's in the problem that you need. And e allows you to cancel out natural log, and natural log allows you to cancel out e, because log base e of e would cancel out. That's a general property of logarithms. So a lot of little things that can go on here with e, but that's where log base e comes from. It actually gives you natural log of x, because a lot of the times this gets brushed over. This whole log e part, a lot of instructors or even tutors will be like, oh, it's just natural log of x. But there is a reason of where this comes from, and it's because our common base was 10, and we have another value of e that allowed us to manipulate some other equations. So we do have that in there. We have that knowledge, and that's pretty helpful to us. And the good news about natural log is because it's a logarithm, it holds all the exact same properties. You don't have to switch up and learn anything new to be able to deal with natural log. It is all working the same. You just have a different base. And what I mean, and I'll give a quick example, is if you look at continuously compounded interest, that is A equals P E R. Oh, might as well write those in the exponent like there's supposed to be R and T. All right, you have this idea of doubling time. And doubling time means you're going to double this value and divide off P. And when that happens, you have 2. Teach you a little secret right now. Doubling time. All right, so doubling time always works out that you double the amount that you're going to invest, then you divide by P, and because it's called doubling time, you're left with 2 on the left side, and then you have E, R, T. And you need to find out, hey, well, how long does it take to double? Fun fact, you need to get rid of natural log, or get rid of E, so you're going to natural log. And that gives you natural log of 2 equals RT. Well, you divide by R. Natural log of 2 over R equals T. That is the formula for doubling time. You can skip all the work, and this equation will always work to find doubling time. Guess what? You want to find tripling time? Change that 2 to a 3. You want to find quadrupling time? Take the 2 to a 4. All right. Instead of having to do all this work every time, because this investment could be something like $5,382, and you're going to double that number just to divide it and get 2. So boom, let's use that formula. And that's one of the applications of natural log, and being able to use it to manipulate equations like E. Sorry for that little rant / detour, but that is useful knowledge, and it's not talked about in textbooks. So that is a special thing that I usually do in my classes. Oops, I just destroyed the camera. All right, so moving along. Let's talk about logarithmic properties. And we can do a couple problems, and this is kind of what we're stopped with for this evening. So you have some logarithmic properties. And I'm not going over the basic ones. I am going over specifically ones that allow you to manipulate equations a little bit differently. So those are product, quotient, and power. So the way these work is if you have a product, that would look something like log base A of m times n. Well, I've talked about it before on the show that if you have multiplication, it holds the same properties as addition. So you actually separate the logarithm into log base A of m and log base A of n. All right, so this is taking a condensed logarithm and expanding it to multiple logarithms. All right, you could do the same thing with log base A of m divided by n, except since now you're dealing with division, your expanded logarithm is subtraction. All right, again, expanded form, single or condensed form. You then have log base A of m to the power of p. Whatever this power is can actually be brought out front. So you have log base A of m, and you just multiply that by p. So this gives you some way to manipulate. And right now it's going to seem really simple with the problems we do. But the reason that we're doing it is because when you get to do equations, you need these manipulations to make your problems a bit easier. Like if you have a bunch of addition, subtraction, or sums and differences, as they are called in textbooks, you'll condense it down to a single logarithm. That way you can then convert it to exponential form. So you have some different equation things that can happen there that are pretty interesting. But these 3 properties are how you either can expand or condense a logarithm. Some textbooks like to say convert to a single logarithm, this being single, and then write your logarithm as sums and differences, which is like this. I prefer condense and expand, but to each their own on how they want to word things. So we have a few different things that can happen here, and none of them are too crazy. So let's talk about condense. The following logs. All right, and when we do that, we could have log base x, or just log of x to the 3rd power. And we'll do another one that's going to actually be a little bit more lengthy. we'll do log base a of x to the fourth plus log base a of y to the 1/2 minus log base a of z to the 7th. All right, so we have two different problems we're going to look at. In the first one, this was actually in my condensed section in my textbook when I was teaching it recently. So if you have something like this, remember, if you just have a power, you're just going to go like this, bring the power forward, so that's 3 log x, and you're done. They're not asking you to give a numerical solution. They're asking you to condense the logarithm. All right, so when you do that, you are done. There is nothing left for you to do. All right, if you see addition, you need to pay attention. In this case, you're paying attention to two things. All right, does my exponent have a power? If it does, that power is now going to come, well, no. I should have written this differently. Big rip. F's in the chat. Let me fix this real quick. Forgot we're condensing this. This needs to be a 4. Plus this needs to be a 1/2. Minus 7. Alright, we fixed the problem. Hopefully you didn't write that down and you just let me write it on the right board so you didn't have to erase it. Alright. Well, since we're condensing the logarithm, we have this all written out. This means we have to work backwards. This 4 needs to come up and be a power. This 1/2 or square root needs to come up and be a power. This 7 needs to come up and be a power. And then you have to pay attention to, I have a plus, and what does plus mean? And I have a minus, and what does minus mean? All right. When I say condense, this means my answer must be a single logarithm. So I know I'm going to have the log base a. I should not have another logarithm. I should have log base a. 4 goes to that, so I have x to the 4th. Plus should be multiplication, so I have y to the 1/2. If you want to write it as square root of y, that is fine. Over, because it's minus, I divide, and I get z to the 7th. I should have a single logarithm. I often see at least 1 or 2 people each year do this. Log base a of x to the 4th, y to the 1/2, over log a of z to the 7th. No. Or, my other personal favorite is to write log base a of x to the 4th, log base a of y to the 1/2, over log base a of x z to the 7th. No. It says condense, which means move it to a single logarithm. All right, so please pay attention to the wording. Please, 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 please. All right, we can also have expanding logarithms. And this is a relatively, these concepts are not super crazy. It's just that if you don't ever see them, or you only see them, once every few years, it makes it difficult to remember how to do. So, again, we have, this time, expand each logarithm. All right, we'll do 2 examples. We'll have log base z of x to the 4th, y to the 1/3, over z to the 2/7. And we'll do another one. We have log base a of square root of x times cube root of y over z. All right, so these aren't too bad. You just need to remember you're looking at everything as being a single logarithm here. You're expanding it out. So x is going to have a logarithm, y is going to have a logarithm, z is going to have a logarithm. All right, in fact, I left a little trick in this problem so we could talk about it. I'll write my equals up here because I'm going to need some room. So I have log base z. It's x to the 4th, so I get 4 out front. I bring x plus 1/3 log base y. I don't have enough room to my side, so minus log base z minus 2/7 log base z of z. Anytime you have log base z of z, so the base and the of are the same, guess what happens? This cancels out, and you're done. All right, so it should be minus 2/7 up here. You know, I don't know, man. I just make up the problems. But I wonder that myself sometimes, and I'm a teacher. So, you know, how do people come up with these problems? You know, sometimes it just be that way. All right, if you have these values and you see square root and cube root, please remember square root of x is the same thing as x to the 1/2. Cube root of x is the same thing as x to the 1/3. All right, I put them in there just so that way you could get a reminder of how that works. And again, you're expanding these out. So you have, you're going to have 1/2 log base a of x plus 1/3 log base a of y plus log base a of z. All right. Again, these ones you're just really needing to pay attention to. My multiplication changes the addition, my division changes the subtraction, and please bring the power out front. All right, it's not terrible. You're just following the properties, which again, if you need to take a look at the properties, they are right there. All right, that is the basics of exponential and logarithmic properties. It was nice getting back to a Math Man Monday. It has been a hot minute since I've gotten to do one, as I get tied up with my camera, just because of a bunch of things going on in life. So I'm glad I could get on tonight and, you know, have one out there. I will be posting this video to YouTube, hopefully either tonight or tomorrow. If you enjoyed the content, always feel free to hit the follow button. If you're watching on YouTube, feel free to hit the subscribe button, leave a comment if you have questions. If there's topics you'd like to see, post in the comments or hit me up on Twitter at Blaze McBain. Other than that, it has been fun. I'm going to switch over to some games here in a few minutes. I'm going to get all my boards and everything cleaned up, and I should be back